Welcome back, data engineers. Today, we are unlocking the ultimate secrets of Apache Spark performance by mastering the Catalyst Optimizer and the Tungsten execution engine. Let's get started. Welcome. When you write Apache Spark code using data frames or SQL, you aren't just running raw, line-by-line instructions. Instead, you are leveraging two incredibly powerful internal engines. The Catalyst Optimizer acts as the brain of the operation, analyzing and drastically improving your logical queries, while the Tungsten execution engine acts as the muscle, processing data at the bare metal hardware level. Why is this so important? Because writing perfect distributed code is difficult. These engines automate performance tuning, converting your high-level operations into optimized native code. Throughout this training, we will explore exactly how these two components work together to make your Spark applications perform lightning fast. Let's look at this high-level workflow diagram. On the far left, we have your data frame or SQL code. As soon as you trigger an action, this code flows directly into the Catalyst Optimizer, which cleans and improves your logic. Once the optimal path is chosen, it passes the optimized query plan down to the Tungsten execution engine. Tungsten then translates this plan into a native execution format that runs directly on your distributed hardware, ensuring maximum efficiency. Let's dive deeply into the Catalyst Optimizer. What is it? At its core, Catalyst is an extensible query optimizer built specifically for Spark SQL and the data frame API. Instead of blindly executing the code you write, Spark uses Catalyst to evaluate the most efficient execution path before a single byte of data is moved. It does this by using two primary techniques, rule-based optimization and cost-based optimization. Rule-based optimization applies strict logical rules, such as reorganizing your filters so they happen earlier in the job. Cost-based optimization goes a step further by utilizing detailed table statistics to intelligently choose the best physical join strategies, like opting for a broadcast join when one table is small. This flowchart breaks down the dual nature of Catalyst. Your input query enters the optimizer and splits into two optimization streams. On the left, rule-based optimization tackles logical structures, ensuring actions like filter pushdown occur. On the right, cost-based optimization evaluates the statistical costs of different physical operations, specifically determining the optimal join strategy. Both of these powerful analytical streams converge at the bottom to produce a single, highly optimized plan. How exactly does Catalyst do its job? It follows a strict, four-step execution pipeline. Step 1. Your code is parsed into an unresolved logical plan. This step merely checks if your code is syntactically correct. Step 2. Spark checks your column and table names against the underlying catalog to validate that the data actually exists, generating a resolved logical plan. Step 3. The Catalyst Optimizer applies its extensive rules to reorganize the query, creating the optimized logical plan. Finally, in Step 4, Spark generates multiple physical plans, runs them through a cost model, and selects the single most efficient physical plan to send to the executor nodes for processing. Follow the journey of your code in this pipeline diagram. Starting on the left, the raw code becomes an unresolved logical plan. As it moves right, it passes through the catalog check to become a resolved logical plan. The real magic happens next, as optimization rules transform it into the optimized logical plan. Finally, after passing through a cost evaluation model, it emerges as the ultimate physical plan, ready for execution. To master Catalyst, you must understand two of its most critical optimization rules, predicate pushdown and column pruning. Imagine you are querying a massive multi-terabyte table, but only need users over the age of 30. Instead of loading all that data into memory and then filtering it, predicate pushdown pushes that filter operation directly down to the storage layer, such as a Parquet file or a backend database. Similarly, column pruning ensures that Spark only reads the exact columns you explicitly select, completely ignoring the rest of the dataset. Together, these two techniques drastically minimize the amount of data transferred across your network and reduce disk I/O, saving massive amounts of cluster compute time. This visual demonstrates how data is reduced before it even hits your cluster. At the top, we have a massive data source. Thanks to the Catalyst filter in the middle, two things happen simultaneously. Column pruning strips away unnecessary data width, and predicate pushdown strips away unnecessary rows right at the storage level. Consequently, the data footprint arriving at the Spark executor memory at the bottom is just a tiny fraction of the original size. Once Catalyst selects the absolute best physical plan, the Tungsten execution engine takes full control. What is Tungsten? It is Spark's internal engine designed explicitly to maximize the efficiency of your underlying hardware. In older big data systems, the Java Virtual Machine, or JVM, created massive performance bottlenecks due to unpredictable garbage collection pauses and slow object serialization. Tungsten solves this by managing memory directly off-heap and utilizing highly optimized binary data structures. By taking control away from the standard JVM memory manager, Tungsten effectively turns Spark from a standard Java application into a hardware-optimized processing powerhouse. Here we contrast the legacy approach with Tungsten. The top path shows a standard JVM application burdened by garbage collection overhead, inevitably leading to slow execution. The bottom path shows the Tungsten engine completely bypassing this. By utilizing off-heap memory management and keeping data tightly packed for CPU cache registers, Tungsten achieves incredibly fast, consistent binary processing. The crown jewel of the Tungsten engine is a feature called whole-stage code generation. In traditional databases utilizing the Volcano iterator model, processing a query involves passing data row by row through a complex tree of operators. This results in millions of expensive virtual function calls. Tungsten bypasses this entirely. Instead, it takes your Catalyst physical plan and fuses multiple operators together, generating highly optimized Java bytecode dynamically at runtime. By collapsing the query into a single function, Tungsten keeps the data inside the CPU registers as long as possible. This breakthrough allows Spark to achieve execution speeds that rival handwritten, low-level C++ native code. Look at how whole-stage code generation collapses complexity. Normally, your physical plan consists of isolated operators like filter, project, and aggregate. Moving data between them is costly. The whole-stage code gen block acts as a compiler, fusing all these isolated steps into one single optimized Java bytecode function. This singular function is then sent directly for lightning-fast CPU execution, eliminating intermediate data handoffs. Let's apply this theory to a real-world use case, processing a 10 terabyte e-commerce ETL pipeline. You need to join billions of daily transactions with a customer reference table. Without optimization, a naive execution would trigger a catastrophic network shuffle, inevitably crashing the cluster with out-of-memory errors. But here is where our engines shine. First, Catalyst steps in. It automatically pushes date filters down to the storage layer so we only read today's data, and it intelligently selects a broadcast hash join because the customer table is small enough to fit in memory. Then, Tungsten executes this heavily optimized plan using off-heap memory and generated bytecode. By avoiding network shuffles and JVM garbage collection pauses, a job that would otherwise fail completes flawlessly in just minutes. This architectural diagram illustrates the real-world pipeline. The 10 terabyte sales data first hits Catalyst's filter pushdown, drastically reducing the payload to 50 gigabytes. Catalyst then pairs this with a small customer table using an efficient broadcast join. This optimized blueprint is handed to Tungsten for off-heap execution, rapidly producing the final aggregated dashboard without ever overwhelming the cluster's network or memory. As a senior data engineer, you must verify these engine optimizations using the explain plan. By calling the explain method with the parameter true on your data frame, you can inspect the exact parsed, analyzed, optimized, and physical plans that Catalyst generated. It acts as your diagnostic roadmap. Additionally, be sure to leverage adaptive query execution, or AQE, which takes Catalyst a step further by adjusting physical plans dynamically at runtime based on actual data statistics. Master these concepts, and your Spark applications will be unstoppable. Please invite your colleagues to like, subscribe, and visit quicktechie.com for premium certification prep, including Q&A banks, full ebooks, audiobooks, full-length training, and interview guides. See you in the next session. This final workflow is your best practice checklist. Always run explain true on your code to inspect the optimized and physical plans. Ensure you enable AQE for runtime tuning. Use these insights to monitor the Spark UI and iterate on your design. By following these steps, you will achieve total mastery of Apache Spark with quicktechie.com.